Hello everyone, today I would like to show you how to work with line joints in Karamba3D. Line joints can be used to connect shells with each other, and to demonstrate this I generated this little example which consists of a floor and a wall, and my aim is to introduce here a line joint between the upper wall and the floor. The whole definition looks like this. First of all, here is the geometry input. It consists of 4 surfaces, 2 floor and 2 wall surfaces. They get meshed here using the mesh B-reps component, and here's the conversion from mesh to shell. In order to have a more realistic example, I specified here wood as the example and a thickness of 10 centimeters for all components of the structure. To make the structure stable, one needs to specify corresponding supports. For this I used the user objects which have been created by Georg Lobe. They can be used to select from a list of points, those which specify a certain condition, like for example vicinity to a surface. And so in using these components it's very easy to specify here the points here and here as support points. The supports here at the base are only blocking degrees of freedom in Z direction. Then we need some loads. For this I specified first of all dead weight, and in order to be able to demonstrate the effect of this line joint here, I placed here on top some beams and attached to those beams a constant block load. Now here comes the line joint. It's a rotational joint about this axis here. In order to specify this line joint, we need to first of all input the line which connects all those nodes which should be part of the linear joint. I again select the points with this user object here, create a polyline out of them and feed them into the line joint component, which can be found here, by the way. Then I need to specify on which elements the line joint shall be placed. In my case, it should be attached to the wall. And now the question arises how to specify whether it's the upper or the lower wall on which the line joint shall be attached, and that's done using the orientation of the line joint. You can see the local coordinate system of the line joint here. Red, green and blue corresponds to the local X, Y and Z direction. And by convention, the line joint is attached to those shell elements to which the y-axis is pointing to. So in my case, the y-axis is pointing upwards, so the linear joint gets attached to this piece of wall here. In case of very complicated linear joints, because they can be curved, they needn't be straight. So in case of curved line joints, it might happen that this y direction that you specify at some points is parallel to the x-axis of the joint, which is given by the direction of the this input curve here. And in that case, this set orientation is used as a backup. And then another case can happen if you have many different walls attaching to one line. In such a case, it's possible to define here an angle range. By default, that's 45 degrees. And this means that all shells within a range of plus minus 45 degrees of this Y orientation get selected for adding this line joint. CT and CR can be used to specify a distributed joint stiffness. T stands for translation, R for rotation. So in my case, I specify here a rotational stiffness about the x-axis of 1000 kilonewton meter per rad. And the degrees of freedom of the line joint can be specified here via this radio button box or via this input here. I remove this. So here I have now a joint without any degrees of freedom. This would be now the joint where a rotation about this axis is possible. And if I reduce the stiffness, of this spring here, you see that the wall more and more tilts under the horizontal load. You can not only specify the degrees of freedom here via the radio buttons, but also parametrically. If you right click on the component, you can click here on expand radio list, and this allows you to specify the degrees of freedom also here via a set of numbers. Tx is 0 and so on. In Karamba, line joints or joints in general are realized by adding an additional degree of freedom into the structural system. And this may lead to peculiar effects, especially if you have line joints which slightly overlap. I would like to demonstrate this here by splitting the polyline into small pieces via this explode component. If I feed now these line pieces into the curve input, I now get 10 line joints instead of 1. And these line joints overlap at their endpoints. And this means that these degrees of freedom are not fixed, which gives me here a warning that there are 9 rigid body modes in the system. This corresponds to the 9 overlapping points of my line joints. So if I remove them and make one line joint again, this warning vanishes. Thank you very much for your attention. Goodbye.